Part 7: The Forest's Decision Engine. How the forest chooses what lives, what waits, and what it sacrifices. This is where your series evolves from "the forest is intelligent" to "the forest is constantly making trade-offs under pressure." That idea is huge. Part 7: The Forest's Decision Engine. How the forest chooses what lives, what waits, and what it sacrifices. What if the forest's greatest intelligence is not just that it connects, signals, remembers, or recovers, but that it decides, not with a brain, not with a commander, not with a plan written in words, but with trade-offs, energy trade-offs, water trade-offs, risk trade-offs, growth trade-offs, defense trade-offs, survival trade-offs. This is Part 7, the forest's decision engine. And if the earlier chapters revealed the network, the signals, the memory, and the timing, this chapter reveals the hardest truth of all. Every living system survives by choosing what it can afford. A forest is not a machine with infinite power. It runs on budgets, carbon budgets, water budgets, nutrient budgets, time budgets, recovery budgets. And every day, every season, every disturbance forces decisions: grow or conserve, expand or defend, repair or reproduce, invest now or store for later, hold the leaf or drop it, feed growth or feed survival. To us, a tree can look still, but physiologically, it is negotiating constantly. That is what makes this so extraordinary. The forest is not passive, it is an economy. Start with the most basic rule. A plant cannot maximize everything at once. It cannot grow at top speed, defend at maximum strength, tolerate drought perfectly, reproduce heavily, and recover instantly, all under the same resource constraints. That is not weakness. That is biology. Life works through allocation. When conditions are favorable, many species invest more in growth. When herbivores attack, resources may shift toward defense chemistry. When drought intensifies, stomata regulation, osmotic adjustment, root investment, and tissue protection can become more important than rapid expansion. When damage is severe, repair and survival may outrank reproduction. This is the forest's decision engine. Not one choice, but millions of distributed allocations happening at once. Leaves, roots, cambium, seeds, symbiotic partnerships, stored reserves, defense compounds, water flow control. No central authority. And yet, a pattern emerges. That pattern is shaped by one brutal constraint. Energy is finite. Through photosynthesis, plants capture energy and carbon, but what they capture is never pure profit. Some of it goes to maintenance, some to respiration, some to growth, some to defense, some to storage, some to reproduction, some to repairing damage, some to sustaining relationships below ground. And under stress, that budget tightens. Clouds reduce light, heat increases water stress, drought reduces carbon gain and hydraulic safety. Nutrient shortages limit growth. Pests increase defense demand. Disturbance damages tissue and transport systems. Now, the system has to choose harder. That is when hidden intelligence becomes visible, because the forest does not respond to stress by doing more of everything. It responds by reprioritizing. Imagine a drought. To humans, drought looks like one event: less rain. To a tree, drought is a cascade of decisions. How long can stomata remain open before water loss becomes dangerous? Should carbon uptake continue at risk of hydraulic failure? Should growth slow to preserve water status? Should deeper roots be favored over new shoots? Should leaves be shed to reduce demand? Should stored reserves be used now, or held in case the drought worsens? There is no universal answer. Different species solve this differently. Different ages solve it differently. Different soils, climates, and histories produce different strategies. Some species are more conservative, slower growth, stronger survival under scarcity. Some are more aggressive, faster capture when conditions are favorable, but greater vulnerability under prolonged stress. Some strategies work in one climate and fail in another. That scientific variability is not a problem. It is the point. Because the forest's decision engine is not one algorithm. It is a library of survival strategies competing, cooperating, and adapting in real time. Now add herbivores. An insect outbreak is not only tissue damage, it is a budget crisis. A plant under attack may alter chemistry, produce defensive compounds, shift signaling, recruit indirect defenses through volatile emissions, or change growth priorities. But defense is not free. Resources used for defense are resources not used elsewhere. And this creates one of the deepest biological trade-offs in ecology: growth versus defense. Grow too fast with weak defense, and you become easy to exploit. Defend too heavily all the time, and you may lose growth and reproductive advantage when threats are low. So the forest must do something even more sophisticated than defend. It must defend at the right intensity, at the right time, in the right tissues, under the right conditions. That is not random reaction. That is conditional strategy. The same logic applies to entire ecosystems. After disturbance, a recovering forest may invest heavily in fast colonizers. Later, as conditions stabilize, longer-lived species rebuild structure. In nutrient-poor environments, slower cycling and conservation strategies may dominate. In richer or recently disturbed environments, rapid turnover and opportunistic growth may be favored. This is decision-making at ecosystem scale, not conscious, but emergent, a system selecting pathways through constraints. And here is where the story becomes cinematic. Because under stress, the forest is not simply choosing what to grow, it is choosing what to sacrifice. Some leaves are dropped, some branches die back, some seedlings fail, some symbioses weaken, some patches burn, some species decline. Some pathways shut down to protect the whole. From a human perspective, this can look like failure. In ecology, it can be survival logic. A system that sacrifices nothing under stress often collapses all at once. The forest teaches the opposite. Selective loss can protect systemic continuity. That lesson appears everywhere in biology. Pruning, dormancy, abscission, localized defense, patch dynamics, succession, compartmentalization after injury. This is not the absence of resilience. This is how resilience works. Now zoom out, because this may be the most uncomfortable lesson for human systems. We say we want resilient organizations, networks, and cities, but many of our systems are designed to avoid trade-offs until crisis forces them. We delay maintenance to preserve short-term output. We underinvest in redundancy to maximize efficiency. We cut buffers to improve performance metrics. We reward visible growth and punish invisible resilience. And then, under stress, we act surprised when the system has no decision engine left, no reserves, no fallback mode, no protected core, no graceful degradation, no capacity to sacrifice small things to save big things. That is not resilience. That is a system optimized to look strong until it breaks. The forest offers a harder model. Build systems that can make good losses, not just good gains. In cybersecurity, this means segmentation, containment, failover, isolation, and recovery priorities, accepting local shutdowns to prevent total compromise. In supply chains, it means alternate sourcing, inventory buffers, modular substitutions, and service-tier decisions under scarcity. In organizations, it means protecting critical teams, reducing non-essential load during stress, and slowing growth before burnout becomes damage. In cities, it means designing for graceful failure. Drainage overflow plans, distributed power backups, heat shelters, emergency routing, and priorities for vulnerable populations. The forest's question is always the same. What must be protected first? What can be delayed? What can be sacrificed without losing the system? What must never be spent, no matter how attractive the short-term gain? That is the decision engine, and every resilient system has one, whether it is explicit or not. Now, return to the forest, because all the earlier parts of this series converge here. Signals matter because they inform allocation. Memory matters because it shapes strategy. Timing matters because decisions made too early or too late can fail. Diversity matters because more strategies exist within the system. Recovery matters because decisions determine what can come back. This is why the forest can seem both chaotic and intelligent. It is not following one perfect plan. It is constantly rebalancing. Across scales, across species, across seasons, across disturbances, across generations. A seedling's choice is not a canopy tree's choice. A wet year's strategy is not a drought year's strategy. A burned patch's priorities are not an intact patch's priorities. And yet the system persists, Because decision-making is distributed, adaptive, and constrained by reality. That last phrase is everything. Constrained by reality, not by wishful thinking, not by image, not by slogans. Reality, water availability, carbon gain, nutrient limits, heat load, damage rates, recovery, capacity. The forest survives because it does not negotiate with physics. It negotiates within physics. That may be one of the most profound lessons any system can learn. So, what should we learn from the forest's decision engine? Build systems that allocate honestly. Know your critical functions. Know your reserves. Know your non-negotiables. Know what you can pause. Know what you can lose. Know what you must protect under pressure. Train for trade-offs before crisis. And never confuse maximum output with maximum resilience. Because when stress comes, the question is not whether your system is impressive, the question is whether it can choose well. If Part 3 was the recovery code, Part 4 the signal layer, Part 5 the memory system, and Part 6 the time machine, then Part 7 is the core processor, the decision engine, the hidden logic of survival, the budget behind resilience, the trade-off system beneath every living future. And once you see it, you start noticing the same pattern everywhere. In forests, in companies, in infrastructure, in institutions, in families, in yourself. The strongest systems are not the ones that avoid hard choices. They are the ones that make them early, honestly, and in the right order. If this changed how you see forests, resilience, and intelligence, like this video and subscribe to Hidden Nature Science TV and Kiosh TV, because the next lesson from the forest may not be about how life survives stress, but how life builds wisdom from constraint.